First Spin. Welcome to First Spin, a show where I learn how to use the Parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of Whisker and Roy.
Me.
I'm
I'm way more helpful than Roy. Yep.
I'm super helpful. Without me, there would be
The only
no
person
noob.
you're helping is yourself.
Oh ho ho ho. I'm okay with that. So let's file in line, folks, and
She's doing it again.
and start with directives.
Well, you mean finished
Or
directives?
finished
We
directives.
covered most of them last week.
You're right.
Yeah, we sort of had to truncate the end of the show there,
Ha ha ha.
though. Oh,
Let's not
man.
go round and round this situation.
I'm floating in puns.
What a
So-
constant barragement.
We're supposed to explain file, I guess.
So file is actually pretty darn easy.
Uh-huh.
You remember last week Whisker showed you how you could do a string of bytes in the DAT section?
Yes.
Well, file is very similar, except you put the word file instead of byte,
Mm-hmm.
and then after that you put the name of a file
Can I ask
On-
something?
on. Okay, go ahead.
You
Does that include,
ask something on
does
this
it-
show?
Yeah, I know.
Really breaking the mold here.
I know. Does this include music files, like wave files?
It's any file.
Any
it's
file.
the name of a file on disk that the project is going to load. So at compile time, it's going to load that file and byte for byte stick it in memory right at that location in memory where the label is at in the DAT section.
Oh, I see.
So the one thing to be careful of is that file can only be up to however much memory you have available. In the propeller, it's a maximum of 32K. However, you probably can't have a 32K file because then you wouldn't have any room for any of your code.
Right.
So typically you use fairly small files. You could have a wave file in there, and there is actually a couple of objects on the object exchange that will play a wave file in that fashion.
Mm-hmm. I've
there
actually
you
used
could-
one.
Yeah.
Mhm.
So, or you could have a file that's a data table of numbers or whatever you want. It could just be, you could have an image, a bitmap image in there, and then if you used it with the graphics
Oh.
code that's available on the object exchange, you could display that on the screen.
Can the file change constantly?
Well, the file gets included when you compile the program.
Oh, so it would have. Okay, I get it. All right.
So you could
Right.
change it between compiles and then recompile, and then it would load in the new version of the file when you
Right.
compiled the file, when
Okay.
you compiled your spin program.
So then I have a question.
No, technically, it's in memory, so is there
Well,
ways to sneak around and
Well,
change
yeah,
it?
it's just the same as if you had in the DAT section, if you had the string with the byte declarator in front of it, right? Once the file is in memory at that label, you could, using that label, modify the data in the file.
And you can pick up where it starts by doing a pointer to it.
Right.
Oh.
The same. It's the exact same as the string example from last week.
Question. So some of these things, obviously, they get dealt with at compile time. Is there a way to get your code to recompile? Can you code into your code the ability to recompile something?
Well, not.
Or is that too
really.
meta?
Well, it's a little too meta because the compiler that you're running to compile this stuff is running on your PC. And the propeller normally doesn't have a compiler built into itself. There are some people that have written some code that would actually compile spin
Mm-hmm.
while running on the propeller.
Mm-hmm.
But it requires more memory, so it has a external memory.
They're-
I see.
They're
SD
very
card or
weird
something.
people. We don't invite them to the dinner parties.
I wouldn't say that. They're
That's not very
Other-
nice.
nice folks,
Okay, we'll invite them to the dinner party, But we're not letting them in the kitchen because they will try to make the dinner, cook the dinner.
That'd be so awesome, though.
Well,
I mean, that's a little disturbing.
I know. I happen to know, like, one of Chip Gracie's goals for the Propeller 2 is to be able to compile and run and edit code right on a Propeller 2.
That'd be cool.
So
I was doing that in like 1982 on my Commodore 64.
Right, and that's kind of
Commodore
his goal.
64.
He wants to have it be a self-contained computer, essentially.
I see.
And with the Propeller 1, it's a little tough to realize that because Spin is such a fully featured language that a compiler to compile it takes up most of the memory.
Mm-hmm.
So in order to do that, you have to use something like an SD card or some kind of external hardware that's hooked up to the Propeller.
Sure.
And then you can, run the compiler program, the Sphinx compiler, which is the one that's out there available on the Parallax forums and Object Exchange, I believe.
Mm-hmm.
And you read from the SD card the program you're going to compile and then send the results back out to the SD card.
Mm-hmm.
And then you can run the compiled program after the fact without the compiler being in the Propeller. But that gets a little, meta.
Right.
Now, what you could do pretty simply, I mean, we say simply, this is a little bit advanced, but whatever, is you could use your file to have a little bit of code in your own little language, right? And your Spin program is an interpreter machine for that language. So it can read the commands in out of that file and act on what it sees in that file. Right. So you could make a little interpreter to do this kind of thing.
I see.
Right.
It's kind of tricksy.
You could make a simple language that could be compiled and run all within the Propeller, but it wouldn't be the same as the Spin language without, you would have to do something more simple. For the Propeller 1, without having any kind of external memory or external hardware, you would need to have something be fairly simple in order to be able to edit and compile and run all on there. And like Whisker said, probably something that's just an interpreted language would be easier.
Gotcha. Okay.
So now that we've beaten file into the ground,
registers, cha-ching.
To move on to registers,
which actually I am quite familiar with. Quite a few of these. Yeah.
Well, you've already used dir a, in a, and out a,
right? And
probably CNT also.
Yes, tons of times.
I'm an elitist. I only use outb.
Well, if you use outb, it doesn't really do anything.
Don't judge me, Roy.
So dirb, inb, and outb exist as registers, and you can store values in there.
You can?
But they aren't physically connected to any external pins or anything.
We tease about them not being real, but they are real, and you can use them. If you were to set a 32-bit number to your outb, it's going to hold that value until you come back and look at it again.
I see.
Right.
So you can use it as a very quick way to store numbers and do stuff to them.
I see.
Right.
So we'll go quickly over this then. Dir A is to determine whether or not the thing is an input, the pin is an input or output.
Right. And there's 32 bits in dir A and one for each pin, and 1 equals an output and 0 equals an input.
Right. So you can use binary to set all of your pins at once. Bam.
Right. Or you can set a section of them using the ... notation inside of the brackets.
Correct.
Right, so 1.3 will set the
pins 1 through
3. Yeah.
Yep.
And dirb isn't really useful in that sense, but you could use it to hold a long and to work on.
Right.
I see.
And one possible example is you could set up dirb to equal, a working value that you're setting all the bits on however you want programmatically, and then you could copy it from dirb to dir A to actually apply it to the pins.
So it's also like mini memory.
Yep.
Yeah,
that's what a register is.
All of these registers are actually mapped to addresses in the cog memory.
Ah.
And they're all at the end. The last 16 values.
Oh, these are the special registers.
Yeah. Well,
right.
they're all special purpose registers, but all of the memory in the cog are called registers. All 512 longs in there are registers, as well as being memory that holds your code or data, right?
Okay.
And the last 16 are these special purpose registers.
Okay.
That are labeled here. And that's why you can just use dirb to hold a value, because it's actually got a memory address that it's equivalent to.
Right.
It's just not connected to any hardware that goes to pins outside like dir is.
Which isn't that big a deal.
Right.
Right.
And so the same thing is true for inb and outb.
So then, okay. So then
those are read only. So hey,
in is about like stuff that's going into that pin, and then out A is stuff that's coming out of that pin.
In A is to read the states of the pins. Out A is to set the states of the pins.
Right. So it's kind of the opposite of what you said, Addie. Because in A is going to read whatever the state the pins are in. And then out A, like I said, is going to set the pins to high or low based on out A's ones and zeros.
Yeah, that's like sending. So it's in would be receiving, out is sending.
Right. But the way you worded it was a little unclear. So we just wanted to make it.
I think Addie's a little unclear in general.
Thank you. Thank you. Let me truncate that thought right now.
She already knows this. You know how to do this.
Out A that sentiment.
So you've already written some code to using these dir A, in A, and out A.
Yeah.
Mostly out A and dir A, so that you could blink your LEDs on your heart. And also a little bit with the XB stuff.
Oh, that's right. Like out A equals 1. I get it. Yeah.
Right.
Okay. And I've used CNT quite a bit too, and we pretty much beat CNT to a pulp a while back in terms of my personal epiphany.
Right. So. It's just the system counter register, and it holds the current system counter value, which updates once every clock cycle.
Right.
And use it with wait count to wait an X amount of time.
Right.
Stuff like that.
Gotcha. So now we go into counter A, which I actually have used, but it was with the servo, the RC servo. And I do remember not fully understanding that.
So one thing just to say it up front, there are actually 2 counters in the propeller cog. So A and B in this case are both actually there and do work, and they're connected to hardware. Unlike the in A, out A stuff.
Right.
And B, in B, out B, those aren't both there, but in the case of the counters, there actually are 2.
Right.
And these registers, the counter A, B, and then frequency, FRQ, A and B, and then PHS, phase, all 6 of those registers in sets of 3 each are used in conjunction with the counters.
Okay.
So counter A, frequency A, and phase A all work together, and same.
So
with the
basically, there's going to be a lot of detail in this, but CTRA lets you set the mode of the counter. Frequency, FRQA allows you to set how fast it's going, and PHSA is allowing you to actually use a phase lock loop on that to like multiply it and stuff.
Yeah, well, so it's a little bit different, simpler than that, but also a little bit more complex. So the basic idea is, depending on the mode that you set on counter A, the frequency A value, whatever you stick in frequency A, will get accumulated into PHSA based on the mode of the counter. So if you use one of the more simple modes of the counter, which is to just every clock cycle, it copies or it adds frequency A to phase A. That's like one of the more simple modes right up at the top. And if you go to page 95 and then scroll down, and it's actually page 98, has a table of all the different modes.
Let me go to 95 real quick. 95 to 96, you said, for the modes?
And scroll down to 98.
Oh, 98.
Has the chart.
Table 2-7.
Yeah, it has a big chart of all the different modes you can set.
Yeah.
So if you use the first usable mode in there is 00010, which is the PLL single-ended. And if you notice in that first column there, it says accumulate FRQX to PHSX. And the X there is just A or B. And the 1 means it always does it.
Okay.
So if we set up PLL single-ended mode, every clock cycle is going to take the value in frequency A and add it to the value in PHSA. Okay?
Okay.
And PHSA is going to count up and wrap around and count up and wrap around really fast or really slow, depending on the value you put in frequency.
Okay.
And then what happens in PLL single-ended mode is that the high bit of PHSA, the 31-bit, feeds a PLL circuit.
Okay.
And we've talked a little bit about PLL circuits in the past. In the case of this particular counter, the PLL is actually doing a 16 times sequence of the main clock, and then it has every power 2 divider below that. So it's got 16 times, 8 times, 4 times, 1 times, 1/2 time, 1/4 time, 1/8 time. And there's, in the counter mode, you can select what divider you want on the PLL. And this is getting really complicated, but it's actually not that complicated once you've set it up and tried it.
Okay.
But what ends up happening is that based on the value that you put in FRQA, you'll get the pin, the A pin there will output a rate of pulses, right?
Okay.
And it will go faster or slower depending on what you put in FRQA. And also what you put in the counter mode register for setting up the PLL thing. And what the reason why they have this in there is so that you can output frequencies that are very high, much higher than what you would normally be able to output with an 80 megahertz clock rate. You can actually output up to like 128 megahertz frequency.
Wow. That's handy. That's and you're outputting at that frequency, but you got no way to, it's just going on, off, right?
Right. It's driving the pin that you defined as a pin, which is one of the values that's in the clock mode register. Is saying which pin is going to actually go at this frequency. And then you also, like I said, you're setting the value in FRQA you could set it to a really small number, and then it'll go at a really slow rate, right? But if you set it to a really big number, then it'll cause PHSA to cycle really fast.
Okay.
Right? And that causes it to drive the PLL circuit faster or slower. And the PLL circuit then also has the configuration in the clock mode to say which divider should you use to get an end result out on the pin.
Interesting.
Yeah. So, you got 2 of these suckers, right?
Right.
Now, what happens if you set them both to the same pin and use one of the counters to modulate the other one?
Well, if you set them both to the same pin, you'll get some odd results because the pins are both going to get ANDed, or it's kind of weird. What you probably want to do in that case is set one of the counters to one pin and another counter to another pin, and then the secondary pin, the B pin there, you could have possibly feeding back into the first counter. But again, we're starting to get into some really advanced stuff, some of which you can only do in assembly. And some of the modes here are useful from spin, but some of them are less useful from spin because you have to do really precise timing things. And in order to do that, you have to use PASM. And you sort of do a little bit of PASM code mixed with configuring the clock the right way. And you have little tight loops setting values on these registers over and over again to produce the result you want. But,
now, with that said, CTRA and this little family here is a very, very easy way to get high timing accuracy on pins toggling on and off for just a couple of lines of code in spin.
Yeah. No, we're about to get into some of the other modes which are useful in spin or PASM, and they're a little bit more specialized, but they're also able to work at very low rates or very high rates depending on what you're doing. One of the useful ones for hardware things is the positive edge detector and the negative edge detector.
Can you explain to the folks what those are?
So what positive edge detection means is that when you have a pin that is in the low state and goes high, right? That means that it's got a positive edge. It went from low to high. And that's different than just detecting that it's positive, right? Because
you're not detecting the state, you're detecting the change of state.
The change of state, right. And if you see in that chart there, the little notation next to it, it's got A1 and not A2. And if you look at the little notes, the A1 means the input of that pin 1 clock away, and A2 is 2 clocks away, 2 clocks delayed. And that it's kind of advanced there, but basically all it's saying is that 2 clocks ago it was off. That's what the little exclamation point A means, is not A. And then 1 clock ago it's on. So that's a positive edge detection because it was off and now it's on.
Yeah, you could use these to debounce buttons then.
You can, although debouncing is sort of a combination usually of hardware and software, because some debouncing will go so fast that this won't even detect it. So you would use capacitor or something for that. But yeah, you're right in that you would use this to just detect when you went from not high to high, and conversely the negative edge is if it was already high and you're going to low.
I think Addie just fell asleep and hit herself in the face with her microphone.
I did not. But I did have a question.
So just to finish up the discussion of those two, what happens is when a pin changes state from low to high or high to low, that's when the value that's in frequency FRQA will get accumulated or added to the phase PHSA register. So every time you get a positive edge detection, it will increment the phase register with the value that's in the frequency register. And typically with these, you would set the value to be 1 in the frequency register, And then the phase register would just accumulate how many times the positive edge occurred.
Now, okay, so what I wanted to do, because I just pulled up my RC servo code, and it's essentially an RC servo driver, I guess. And what it has is it's CTRA 30.26 colon equals %00100. So that sounds like the control mode was 00100, which according to this table is NCO single-ended.
Right, and what NCO stands for is numerically controlled oscillator.
Okay.
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 And so remember when we were talking about the PLL single-ended earlier, this is similar but a little bit different, and let's cover that real quick.
Okay.
So every clock cycle in this mode, the NCO single-ended, the frequency X value, frequency A, will get accumulated to phase A. So it'll add every clock cycle, it'll add the value. When the high bit of PHSA is on, then the pin will be on. And when the high bit is off, the pin will be off.
Okay.
In this mode.
Okay.
So the top, the bit 31 of that PHSA register, which is counting up every clock cycle based on the frequency A register. Do you understand what's happening there is that you're getting a square wave output based on the value that's in FRQA.
Okay. I guess
so
I
that's
do.
what that's doing.
Okay.
So imagine you had 1,000 in FRQA, and it's going to add that to PHSA.
So every
clock cycle.
Every clock cycle it adds 1,000 square waves, I guess.
No, it just adds 1,000 values. It just the number 1,000 gets added to PHSA.
Okay.
PHSA after one time will be 1,000. After two times, it'll be 2,000.
Yeah.
After three times, it'll be 3,000.
Yeah.
Eventually, it will add up to the maximum number that can be in a 32-bit value.
Yeah.
And the halfway through that, the top bit, because it's a binary representation, halfway through your maximum value count, the top bit will turn on. So bit 31, when you have a number that's greater than 2,100,000,000, whatever, the halfway point of the maximum 32-bit value, that's what will cause the bit in bit 31 to turn on, which in this case causes the pin to turn on.
Okay.
And then after it keeps counting up, and eventually it gets to the maximum value that you can hold in a 32-bit register, and it will wrap back around to 0.
Okay.
So when it wraps back around to 0, pin 31 the bit 31 is no longer high, so the pin goes back low.
Oh wow! So that's a pretty quick process.
Well, it can be. I mean, if you put in a very small number, it'll take it a really long time to count through all 4 billion numbers, right?
Right.
If you put 1 into frequency A, it will take it almost 54 seconds to count from 0 to 4 billion and wrap around. So what you would end up with that is you'd have 27 seconds of the pin being low, and then 27 seconds of the pin being high. And then it would go back to low again after that. And that's if you put a 1 in frequency. But if you put a really big number in frequency, then it'll go faster.
Okay. And that's the thing, like this code has frequency, but it doesn't have phase. Is that a problem?
Yeah, right, because you don't actually set the phase yourself.
Oh, it's just something within.
It gets set every clock cycle when you add frequency to it.
Okay.
Because that's the mode that you've put the clock counter into, right? This counter A is NCO single-ended. in that first column there, it has a 1, which means it always copies or adds frequency A to phase A every clock cycle. So whatever value you have in frequency A is going to get accumulated and add up into PHSA. And it automatically takes PHSA and applies the top bit of it to pin A, whatever pin you've set up for that clock counter, which your code I'm sure sets in the counter.
Yeah, it does. It's well. It says counter 8.0 equals servo pin.
Right. So the bottom 8 bits, it's actually really only the bottom 5 bits.
Yeah.
Are setting which pin is going to have this clock counter's output driving it, right? And so that's why that's why you get a square wave output on that based on this setting.
Gotcha.
So how's that for introduction to the counters? Makes sense?
I'm going to have to do some reading on it, I think.
They're interesting.
So counters are a really, really powerful feature of the propeller, and the fact that there's 2 of them in every cog.
Yeah.
So 16 total. It means that you can do some pretty complicated things. And like I said earlier, some of them require you to actually use PASM assembly code to really take full advantage of some of these modes. And there's an app note that Parallax has up on their Parallax Semiconductor website that covers these counter usages and has all kinds of nice block diagrams and charts and a lot of explanation of these various different modes. And I would recommend most people, if they want to learn a lot more about the counters, to go read that app note. It's app note 1.
Cool.
On the parallaxsemiconductor.com webpage.
Cool. And when you're getting into the counters, that means you're on your way to doing some really cool stuff with this chip.
Yeah. Some of the things you can do with the counters, you've already mentioned the driving a servo. You can actually do pulse width modulation to create sound, or to drive a DC motor controller, or there's all kinds of applications for some of these settings.
Cool.
And some of the edge detection and the logic ones can be used for doing things like detecting frequencies, counting some external input's frequency rate, or to generate specific output frequencies, stuff like that, which are useful for working with things like radio signals and whatnot.
Right, good old RF.
I've actually built a little ham radio Morse code transmitter with a propeller just by sticking a little wire on one of the pins as an antenna and using the counter to turn the pin on and off at the frequency that I wanted to have it transmit at.
Right.
All right. So is there something else, Roy?
Well, I just wanted to say that the whole last section where it has all these logic ones are typically used for things like detecting the state of one pin versus another. So you have like, if this pin's high and that pin's low, or if they're both low, or if they're both equal to each other, then do something, count up a value. And so those are useful for various things, like if they're holding 2 different buttons down or something, you can detect that and things like that.
Cool.
All right, we safe to wrap things up?
I think so.
Awesome. All right, you guys can find this show every Tuesday at firstspin.tv, and of course you can talk to Addie and Roy and I every day in the Tymkrs IRC. You can find out information on tymkrs.com. There's a link right on the page there.
Join us.
All right. We'll see you guys all next week.
Bye.
Bye.
Bye.